Okay, welcome to the first session of Contributed Talks, MFPS number 40. I was here for MFPS number 1, so it's a thrill to be back in my hometown of Oxford, where I did my PhD many millions of years ago. And it's great to see that the area is still vibrant. Lots of new young people doing great work. But the first talk today is Inferentialist Resource Semantics by Alexander Gheorghiu.
Hello, everybody. Thanks for being here. So this is part of a program of research that we're doing on this thing called inferentialism, which is a sort of new conception of logic. And this is one of the applications we're thinking about, how to do some modeling using this account block. So this is joint work with David and Alex. Okay, so first I'll tell you what we mean by resource semantics and why we care about it. Then about proof-theoretic semantics, which is the logical formulation of inferentialism, and then how we do modeling using proof-theoretic semantics. Okay, so resource semantics is all about trying to understand systems. And so, what is a system? Well, we think of it as a collection of locations, so seminar rooms, lecture theaters at the university, of resources, people, for example, that are in certain rooms but not in others, and relative to which processes execute. So after lunch, all the resources move into a certain lecture. In more complicated systems, you want resources to consume, create, move, combine, have all these nice things you can do with them. And there are several examples of this. So hospitals, universities, computer communication networks, data that gathers, aggregates, splits, memory locations, these kind of things are all examples of resources, processes, and applications. And all of these things are systems, and we want mathematical tools to be able to understand, represent, and think about. So the canonical example is probably the vending machine. So you have two locations, you have a customer and the vending machine itself. Your resources are money and chocolate bars. And you have a process that says if the consumer gives up 200 kroner, one chocolate bar. Okay. So the mathematical tool to reason about such systems is called resource semantics. Okay, so what we mean by that, and it's not perhaps a formal definition, but our conception of it is an interpretation of formula. It's a formal. Sorry, I heard that it's very hard to see the image from like the if somebody knows how to operate it. Yeah. That's oh, okay. Someone else was saying, okay, it's that sort of. Oh, there's the thing, right? Sorry. Perfect. Okay, so we want to. So what we mean by resource semantics is an interpretation of formulae in terms of the system. So particularly about state and process, and in which we can express the behavior of the resources, the process. So this is supposed to be quite general. So we don't really mean to restrict the sense of in which formulae are assertions. You can talk about the system changing as a consequence of some process executing. That's what we mean by higher order in this case, and all kinds of processes that are relevant to your domain, right? And so in particular, we typically require these kind of things. Okay, so there are some examples of this in the literature. So one very celebrated one is the number of users interpretation of linear logic, in which you think of atoms as formulae as resources and implications as the processes. And then there's the sharing separation interpretation of BI, which is, of course, what leads to separation logic. And the big difference between these two is the number of uses interpretation of linear logic is proof theoretic. It's not a crypto model. Whereas the sharing separation interpretation of BI is its delimitation of semantics, or a delimitation. Okay, so they're both very good and very useful, but they have some limitations. So in terms of our notion of resource semantics, the number of uses reading is really all about talking about the dynamics of the resources. So how they move, how processes shift them and change them, consume them. But it doesn't, for example, talk about the structure of the system. Right? So it's very hard to talk about a hospital in terms of living. The sharing separation interpretation of BI is very good at talking about structures, or how different parts of the system glue together. So this is like the stack and the heap, so different heaps and so on in the computer memory. But it's less good at talking about the processes themselves. Okay, so if we are really going to have a good resource semantics according to what we want to be able to do both of these things at the same time. And so we're going to talk about proof theoretic semantics. Okay, so we want a judgment that looks something like this, right? So phi is an assertion describing the state of the system, possibly in terms of the resources, and processes of that system. Gamma is a policy. So by policy, we mean something general that describes the structure of the system, the behavior of the system. Then we have some contextual collection of resources available. So when you supply the policy might specify that you have some additional resources in certain locations. You plug them into the spot, the dot there, and you get the actual collection of resources you have available. And then these calligraphic B's and C's and so on are what you can mean by model in this case. So that a judgment of this form at the bottom here says that if you have the policy gamma, then this set of resources U, and together with C form a model of gamma of that policy. Okay. This is the same thing. So that's our task, to come up with this kind of judgments. And we use proof theoretic semantics. So now I have to tell you what proof theoretic semantics is. Okay, so it's based on this idea of inferentialism, which is a meaning as use conception of logic. And you've probably heard of meaning as use in the sort of philosophical sense. In this case, use means inference, so we can be quite formal about it. And so proof theoretic semantics is this formulation that's been worked on before, arguably since the foundations of proof theory, but particularly by Pravitz and so on. The term comes from Peter Schroeder-Heister. What you're probably used to is denotational semantics in the Tarskian way. We have a model, which usually now algebraic structure relative to which you interpret formulae. What we're talking about now is inferentialism, so it's a different paradigm. So on the left-hand side, you have model theoretic semantics. On this side, you have proof theoretic semantics. The former is a meaning in terms of truth. This one is a meaning in terms of proofs. But proofs are not in a fixed system. So it's a pre-logical notion. You'll see what I mean. Okay, so an example of a model theoretic semantics is Kripke semantics, various logics. And in this case, we're going to talk about base extensions. There are other accounts of proof theoretic semantics. This is the one that's interesting to us now. So again, the word proof here can be a bit misleading. It doesn't mean, fix your favorite proof system. It's really a pre-logical version of proof. Could, for example, just be a set of production rules. So you have something easily algebraic, some sense of inference there. So no logical constants. And so you have in base extension semantics, even though there's a proof theoretic semantics, you still have samples of completeness theorems in the usual way. That's crucial. Okay, so we begin with pre-logical proof systems. These calligraphic B's, and these will be our models. And as I said, they can be, you can think of them as simply a set of production rules. They can be a little bit more complex, they can be a little bit less complex. Crucially, they don't have any logical structure. They don't have any logical constants or any of that kind, so they're illogical. From these, the only important thing is that you can use whatever you choose to be or be there, you define a derivability relation. And that's what makes this proof theoretic. And then you give clauses in the usual way you're familiar to in Kripke semantics. So it can look surprisingly close to Kripke semantics, but it's not exactly the same. And we can talk about that later. Okay, so for example, here are some production rules, and this forms what we call an atomic system or base, logical proof system, and it composes in the way you're used to. So if you had something that produced a P and a Q, you can then get an R. Okay. And so these are some clauses. Now, this system essentially defines intuitionistic logic. So you can also you can add disjunction as well in an interesting way. And the important thing here is the base case. So this is now derivability rather than truth at B. You might be saying to yourself, gee, this looks really a lot like Kripke semantics, but it isn't because of the way disjunction is. And we don't formally know the connection. In fact, to get full intuitionistic logic, you have to have slightly generalized notion of atomic system here. If you just restrict to production rules of these kinds, you get classical logic. And that's even while keeping this extension. So it's more subtle than saying it's Kripke. Okay. So we want to talk about resources, and we want to capture something linear logic-esque. So we're going to move on to our substructures. In this case, our pre-logical notion of proof is very similar, but the way we define derivability is now context sensitive. So in the first case here, you don't have weakenings. This is a non-monotonic logic because we are context sensitive, we're linear. But this is not hard. People familiar with substructural proof theory, it's very standard stuff. So we can capture intuitionistic linear logic by adding to our support relation, this guy, the forcing relation, some multi-set of atoms, which we think of as resources. Of course, when we do actual modeling, that's exactly what it will be. And we can then define a multiplicative conjunction like this. So this is, so the two of the clauses look very similar to the case for intuitionistic logic, the middle two clauses there. Nothing has really changed there, except now this T is added. So when I have a set of resources T for gamma, I add them to my current set S. What's interesting is the treatment of conjunctions, which can look perhaps a little bit alien. And you might wonder, why is this the tensor? Well, first thing you might want to write down is something like the comma clause. And you can do that, but this ends up being more useful for what we'll be doing. It actually ends up being easier to prove science and completeness. It's not apropos of nothing. It's actually just recalling the elimination for tensor. So it might look a bit complicated, but it's fully principled. And this relationship is exactly how it comes out in the completeness theorem. Okay, so now we want to capture all the way through to BI. So we want both the number of users reading and the sharing separation reading. So the difference between BI and linear logic is that we want primitive conjunctions and implications. Right? So linear logic, of course, is a primitive multiplicative one, and then using bang, you can define the additive one, but we now want them both primitive. That defines BI. And because we have two primitive conjunctions and two primitive implications, our data structures are now not multi-sets, but these structures are a bunch of pretty standard stuff in BI and relevance logic literature. But structurally, we're the same. So now, rather than having a multi-set of atoms, we have a bunch of atoms as our resources. And these clauses exactly recall what you just saw from linear logic. So the star is, of course, equivalent to tensor, the magic wand equivalent to multimap, lollipop. And nothing has really changed except we have this substitution inside now because of resources, because our data sets, our data structure is a bit richer. And that recovers the multiplicative fragments, so that recovers the linear logic. We also add now the additives. right? And the big difference here is for the multiplicative case, I put a comma there. For the additive case, I put the semicolon. And the comma is the multiplicative conjunction, left, and the semicolon is the additive conjunction, left. But otherwise, things are very, very similar. So there's a nice bit of symmetry in the system. And what makes everything cohere is between the right and the left is the treatment of the implications. So they make the star cohere with the comma and the meet cohere with the semicolon. Okay, so that's the mathematical foundation. Let's do some modeling. So we came up with this reading where in all these cases, you can see this treatment where you have a non-empty left-hand side. In all cases, you had something like this. So even in the basic case of the intuitionist logic, you can do something like this, except your resources are just carried through all the time. You know, really used. But for linear logic and for BI, you have something like this, and this is quite general. So you can always do this for substructural logics. And now we want to read things as follows. Covering the reading from the beginning. Phi is an assertion about the system. Gamma specifies the policy about the system. S is a set of resources. And B and C are models of the system. So that's the reading we promised at the beginning. That's the one we want to deliver. And we can do that quite generally. Yeah. So in this case now, in the general setup, you have some notion of atomic resources. In BI, we fix that as bunches. In linear logic, it's multisets. Whatever you like, you get different logic. Okay. So here's a general picture of a system. So you have different components. So these are your locations, and they host resources, and there are processes that tell you how things flow between them, and maybe there's some interfacing in between them, which tells you exactly how the output from here matches the input from there. And all of these components are modeled by these atomic systems, the calligraphic B's and C's. Okay. So each component is described by a formula that says what goes on with that component. And then you model the component using a base and a set of resources that support that formula, including the interfacing. And you can then construct a model of the whole system D by taking the union of these component parts, including their interface. So it's quite compositional, and that's nice. And that also means that if I were to look into this component and I realize that's itself a little system, I could then just substitute B4 for B41 and B42. So you get this nice substitution, this refinement of your model. And you can specify them at whatever degree of resolution is satisfactory. So here is a particular instantiation that's relevant, especially to us, because we just came back from Reykjavik. So when you arrive at an airport, you march with your luggage in this way, and then you drop off your luggage, and it goes somewhere, and you don't have to look at it until you land, and you go through baggage control this way. And then you go through various stages, such as passport control, and then departure gate. And at each point, you have to present some resource, your ticket, your passport, some security access control. And this is a quite basic notion of system, but a very important one. This is the kind of thing we want to model. Okay, so just looking at L1, L2, and L3, and we did the whole thing in the paper. Now, you can model them like this. So arriving at the airport, you submit your passport, and what you get, what returns to you is a passport and a ticket, because you checked in, and a whole baggage label that you can attach to your baggage and send it off behind the scenes. So now when the baggage goes through the second location, the label is scanned and it's certified. And if it's not certified, then it doesn't go through. So you exchange your label for a validity certificate. And similarly, your ticket, you scan it on the thing, go through the gate, and it's certified. So these are what the S's. Okay. And so then you can combine this part of the model by saying, well, I pass through phi1, and then phi2 and phi3 occur separately. So we use the separate. Because the resources are not shared between these things. Your passport isn't here and here at the same time. It's only down at the bottom component. And that's what determines all the conjunctions that they use. Okay. So that's a cute little model, and you can again refine it, especially on the aircraft side. There could be a huge checklist that has to be checked, so you can just add that data into the system. Some other component here which isn't relevant to you, but very relevant to the airport guys. Okay, so our thesis and the point of doing this is to use proof theoretic semantics to provide an account of resource semantics that does everything we're interested in particular, encapsulate both number of users and sharing separation interpretations of logic. So it talks both about the structure of systems and about their behavior at the same time, in a way that's coherent. And what makes these two things coherent, the structure and the behavior, is the treatment of the implications and the gen inf. Okay, so in summary, we want to talk about systems mathematically in the same way we talk about programs mathematically to verify properties and security and liveliness of them. We call this work resource semantics. And in this paper, we offer a uniform paradigm, instantiated in particularly with BI and linear logic. You can be more flexible. You could add modalities, actions. And so to do this, we use proof theoretic semantics. So we combine the best of both worlds, the best of proof theory if we're talking about process, and of model, of semantics, we're talking about structure. And doing this, particularly for BI, has some desirable features. So now we just want to formalize it and do it more generally, and do some interesting work.
Yeah, hi, thanks for the talk. There's something that I understand, because I thought that the goal was to combine linear logic with separation, or like the two different kinds of resources that it's have. But in your example, you only have GI connections. So how are you also capturing the?
Oh, so BI extends. So if you take linear logic and you look at just the multiplicative, right, which are really driving your consume, the way you manipulate resources, and you add additives to that in a primitive way, you get BI. So BI, the reason we chose BI is it's already an extension of a primitive set of linear logic. So it's not the case that we're looking to combine linear logic and separation logic. We're going one step further back from that and asking why does separation logic work? Because of the sharing separation interpretation of BI. Why does linear logic work? Because of the way multiplicative connectives operate proof theoretically.
BI already has the connectors from the multiplicative linear logic, right? Like,
yeah.
I guess I'm not understanding how. So how is this different from just BI? Like,
Oh, so I'm using a semantics for BI, but not the sharing separation semantics. Because in this semantics, what's really neat about the semantics for BI, one of the reasons it's so satisfactory to work with is in this case I didn't put them, maybe that's what's confusing. Let's look at linear logic. I actually have two ands. I have the tensor and the comma, and for BI I have four ands, and the comma and the semicolon allow me to talk about structure, and the tensor and the other one allows me to talk about behavior.
Yeah, maybe similar to that question. My thought was, why there's no end and there's no points to it. Talks about maybe that was what I was wondering. If you're talking about separation logic, especially emerging from BI, one of the things that it has in particular is end and points to. Can you put that in?
Yeah, that's just a theory. That's so you take BI and you take a particular model of BI, which is the same as taking modeling a particular theory of BI. Of course, you can do that, but that's the role of this gamma, right? You supply, and you could add, as primitive set of atoms that you have these points rather than P's and Q's. You have, if this points to that and that points to that.
That's just an example. The only basis you start.
No, absolutely not. No. This is just a logical bit, and then the way you instantiate that, like in the airport case, it's just one particular instantiation. If you wanted to model wild programs, you would instantiate it to that system.
Then you also deal with something like fractional commissions, a more refined notion of counting.
I don't know. I'm just a logician.
There's nothing just about being a logician. Any questions?
So I understand right, you're not out these system.
Yes.
But I'm not well. I think that's. I can read them as.
So in all these cases, for all the logics I've shown here, they are of this form. So there are primitive rule systems. Strongly connected to logic programs. That doesn't seem to be essential, right? The point is really this, that you have some pre-logical notion of proof, right? It doesn't have to be natural deduction, which is the kind of format we're working in for legacy reasons. The point is you derive relative to some notion of system, of proof system, a derivability relation. And then you can do that as flexibly as you want. So this is really the recipe you follow to get the basic extensions. Yes. Yep. And you can be we can be flexible about exactly how to specify.
Thank you.